Hey everybody, it's Mr. Gustin back in the physics classroom. Today we're talking about two body systems and the net forces and accelerations that are acting on them. We're on worksheet number 5. Make sure you've downloaded it from Canvas so that you can keep up with it right here. I'm going to do it right on the board. You do it in your science notebook or on worksheet 5. First things first, I'm going to look at this problem and go ahead and draw the forces that I think are acting on each object here. So my picture is drawn in black. I'm going to go ahead and use blue if it stands out. First things first, oh, that's an empty marker. I'll use red. There's the weight force acting on M1, and there's a larger weight force acting on M2. How do I know? I'll call this FG1 and FG2. How do I know it's larger on mass 2? Well, mass 2 just looks bigger in the picture, so I'm going to assume that it's heavier, which means there'll be a larger force of gravity there. I'm going to start there, and here's why. Because I need to then think about the other forces that are acting on it and the direction this whole system is going to accelerate. So let's think. If I were to take this system and let it go, if I was hanging on to it in my hands and I let the system go, which way would it move? Which way would it accelerate? Well, I know that mass 2 is heavier, so mass 2 would pull towards the ground. This whole thing is connected, so if mass 2 falls, that must mean mass 1's going up, and that must mean my pulley's moving this way. So I'm seeing this type of direction. It's going to move this way. What that means is the forces on mass 2, well, Fg must be winning. So the other force acting on it, which is the tension force, pulling it straight up, Ft on mass 2, must be smaller than that weight force on box 2. How do I know? Again, it's accelerating down, so the net force must be down. Let's look over at box 1. On box 1, it's accelerating upward. Well, if it's accelerating upward, then this tension force right here, Ft1 we'll call it, must be larger than the gravity force or the weight force on mass 1. Let's go ahead and make a little inequality symbol. Fg1 is smaller than Ft1, and over here Fg2 is larger than Ft2. Okay? Got it. There's one more thing I know because we just discussed third law pairs. I have this tension force in the rope here. Mass 1 pulls on this rope pulls back on mass 1. Well, that same rope is pulling on mass 2, right? The rope pulls on mass 2 pulls on the rope. This rope is connected to both mass 1 and mass 2. That means that the force of tension acting on box 1 is equal to the force of tension acting on box 2. I can see how all of these forces are related, and I had better make sure that in my picture, Fg1 is the smallest force. I had better make sure I say these two forces are congruent to each other because they are Newton's third law pair. And lastly, Fg2 is going to be the largest force. It's the driving force that pulls the system up on the left side and down on the right side. Let's start answering some of these big idea questions now that we have all of this here. Hopefully you have enough information to answer these questions, but let's see. The first question is, how does the acceleration of M1 and M2 compare? Well, here's a big idea, or a big question, right? Can M2 move without moving M1? Can this box move without moving that? Heck no! Of course it can't move. So, no way. Can M2 move without M1? No. This is going to fall, that's going to go. How do the accelerations compare? They're the same. That's important. The acceleration on box 1 is equal to the acceleration on box 2. That's a pretty big idea. How does the tension compare? We already answered that question. The tensions are the same. They're the same string connected to two boxes. We know it's the same. How does Why do we bend the coordinate system is question number 5 on worksheet 5. I don't like that question. I don't want to answer that question. Here's what that means. That means like up over here is like positive maybe, and then down over here. No, forget all that. We're not going to bend the coordinate system. All we're going to say is that the direction of acceleration is positive. Okay? Whichever way this object is accelerating, we're going to call that direction positive. So over here, up is positive, down is negative because it's accelerating up. And over here, the acceleration is down, so we'll call that positive. That's all that means. We will always call the direction of acceleration positive. It just makes math a little bit easier for us. To find acceleration, is it best to focus on one individual object or the system as a whole? What do you think? Well, I would have to write out some F-net equations to figure this out. So let's do that. I'm going to write out 3 F-net equations for us. The first is going to be F-net on mass 1, then F-net on mass 2, and lastly, I'll write out F-net for the entire system. So I'm going to include all forces in these directions for mass 1, mass 2, and for the system. So let's see. F-net on M1. Well, F-net 1 is equal to the mass 1 times the acceleration, which is equal to all of the forces acting on mass 1. So positive, we have the tension force minus the weight force on mass 1. There's the first F-net expression. The next F-net expression will be mass 2 times acceleration equals Fg2 minus Ft2. Interesting. And lastly, we have the whole system, which is mass 1 plus mass 2 times the acceleration is equal to, oh boy, I need more space. Let's bring it over here. For the whole system, F-net system is mass 1 plus mass 2, because they're in the whole system, times the acceleration, which is equal to, remember, positive if it's up over here, negative, positive if it's down over here. Positive up, positive down. All right, let's see here. Let's start with the positives. Or let's start with box 1. Box 1 is Ft1 minus Fg1 minus Ft2 plus Fg2. This is the entire F-net expression. It even runs off the screen. Now, we simplify it because we know over here that the tensions are equal and they're in opposite directions. We can like exclude these tensions, and we end up with mass 1 plus mass 2 times the acceleration, which is equal to Fg2 minus Fg1. So the question asks, is it easier to use individual objects to find the acceleration of the system, or is it easier to use the F-net of the system? My question to you is, what do you know? Do you know the masses of these objects? Do you know mass 1? Do you know mass 2? If you know those masses, this is pretty darn easy. Because guess what I have to know to solve these two expressions? I have to know the tension force. The only way to know the tension force really is to throw a scale in there and try to measure tension force using a spring scale. I don't inherently know the tension force. And no, it is not equal to gravity in this case. The whole thing is accelerating. Tension does not equal the weight force. No, get that out of your head. This is accelerating. So is it easier to use the individual ones that include tension, or is it easier to look at the whole system that really only relies on mass? It's probably going to be easier to use the system's net force equation to find mass, or to find acceleration. Once we find the acceleration, now we're on question 7. Once we do find the acceleration using some algebra, is it easier to use this equation or these equations to find tension? I mean, it's kind of a silly question, right? Tension force only exists in the individual F-net expressions. So I can't use the system's F-net to find tension. I really should be using one of these two equations when I'm asked to find tension. Okay? These are all of the big ideas when it comes to masses hanging over a pulley. I have my free body diagram. I make sure that I go ahead and use inequalities or equalities to represent how big or small these forces are compared to both objects. I think about the acceleration of the objects. The acceleration is the same, which means that the acceleration in this F-net, the acceleration in this F-net, and the acceleration in this F-net are all the same. I remember to take the direction of acceleration as positive. That way it gets easier when I'm thinking about things going up and down. I write out my 3 F-net equations, and then I can think about and analyze those equations to determine how to solve for either acceleration or tension in my system. That's a lot of information. You have the big ideas. You should be able to go in and solve problem number 2 now on the second half of this worksheet. Good luck. I will see you in class. See ya!